Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. Today we will learn how to add together AC signal and DC voltage, what is DC offset and what is AC decoupling capacitor. So, let's go. If you enjoy practical electronics tutorials like this one, please subscribe to the channel. Don't forget to like the video and enable notifications so you don't miss future projects. Thank you. In today's video we are trying to solve problem of dealing with AC signals in pure DC circuits. If you are new to electronics, this can be very challenging concept to adopt, so let's shine some light to it. First, let's dispatch with syntax and grammar. You might think, well, if there are AC signals, it's only logical that there are DC signals as well, right? If main feature of AC signals is to change direction periodically in the circuit, stands to reason that DC signals flow only in one direction, right? It's logical, but it is not so. So far, so good. Main characteristics of AC signal is that during positive amplitude signal has one direction in circuit, depicted with red arrow, and during negative amplitude it has opposite direction in the circuit, depicted with black arrow. This shift in direction repeats periodically, and number of both shifts in 1 second is by definition signal frequency. Signal also has its amplitude, measured in volts. It is maximum or minimum value signal achieves in 1 cycle. And that is all there is to know about AC signals. As for DC signals, there are no parameters. DC signal doesn't exist, it is just an only output from DC power source, for example, a battery. Okay. Now you may wonder why is all this such a big deal? AC signals goes round and round, and there are no DC signals, so what is the problem? Well, since this entire series is dedicated to transistors and amplifiers, let's draw a quick NPN transistor circuit. We will omit resistors, just for the sake of clarity in animation. Okay, let's introduce our signal at base terminal and see what happens during positive amplitude. Signal goes in the circuit, enters transistor, through base terminal, gets amplified, exits the transistor, and all is good. Now, let's see what happens during negative amplitude. Now signal goes through the battery, enters emitter from the bottom, and exits through base terminal. What the heck? This is totally wrong, signals cannot enter into emitter terminal, they do not get amplified in this way, and base terminal cannot be exiting point for amplified signal, so this won't ever work. Let's further demystify this conundrum. Transistors are powered and operate entirely in DC domain. This means they are powered by DC power source, they can accept, process, and output signals that are only in DC domain. Furthermore, in order for NPN transistor to be properly biased, there needs to be voltage difference between base terminal and ground of at least 0.7 volts. But how do we put AC signal into DC domain? Our goal is to shift or to pull up AC signal so that both positive and negative amplitude now rests entirely in DC domain, and furthermore, rests above 0.7 volts required for to properly bias NPN transistor into active mode of work. Now, let's blow up this schematic and properly mark our AC signal. First, we have positive and negative amplitude of the signal, measured in volts. Next, we have highest positive value of the signal, also called maximum, and lowest possible negative value of the signal, also called minimum. We also have period of the signal measured in seconds. By definition, period is time that takes for the signal to complete one full cycle, and then starts to repeat. And at last, we have frequency of the signal which is inversely proportional to period of signal, and measured in hertz. Also, AC signals can be square, triangle or saw-shaped. But this is irrelevant for our goal. It is also very important to notice that AC signal oscillates around x-axis. X-axis is always referred to as ground, or point with 0 volts potential difference. And at the end, one of the most important parameters for us, is the absolute value between lowest and highest value of the signal, called point-to-point value, marked as VPP, and measured in volts. Don't confuse amplitude of the signal with point-to-point value. They mark two different parameters of the AC signal. When dealing with AC signals, point-to-point value is always preferred way to describe and depict AC signal compared to its amplitude. Now, let's give our signal some values. First, let's give him point-to-point value of 1 volt. This also means that positive amplitude of the signal is 0.5 volts, and negative amplitude of the signal is minus 0.5 volts. Let's assign period of 1 second to our signal, which also means that frequency of our signal is 1 Hz. Signal with this amplitude and point-to-point value is kind of the signal that you would get out of phone jack on your smartphone, with volume rocker at 50%. And no, you cannot use Bluetooth earbuds for this. As we can see from graphics on the screen, our entire AC signal is below threshold of 0.7 volts required for NPN transistor. So, if we were to feed this signal to NPN transistor, we would get absolutely no signal at collector exit terminal, or for that matter anywhere else. Entire signal would pass below 0.7 volts threshold, and NPN transistor would remain in cutoff mode forever. In order to shift our AC signal in its entirety into NPN transistor DC operating domain, we have to add 1.2 volts of DC bias to our AC signal. Now, our AC signal in its entirety is in DC NPN domain. Please have in mind that parameters of our signal have not changed. Point-to-point value of our AC signal is still 1 volt, positive and negative amplitude is still positive and negative 0.5 volts, respectively, with period and frequency of signal unchanged. Only one most important thing that has changed, is that now our AC signal oscillates around new axis, that is 1.2 volts above original 0 volts or ground axis. In technical terms we say that we have added 1.2 volts of DC bias voltage to our AC signal. Or, put it more simply, our AC signal now has 1.2 volts of DC offset. For technical definition, amount of DC voltage that you add to your AC signal is called DC offset. So, if we were to feed this new shifted by 1.2 volts DC signal into our NPN transistor, the signal in its entirety would go into base terminal, got amplified, and at collector terminal we would have our new amplified signal. Okay, so the question is, how do we do this? At this point we would strongly recommend that you watch previous video of this series, episode 23, as knowledge of voltage dividers is paramount to the topic we are about to cover. Now, let's draw simple voltage divider circuit, containing DC power source of 5 volts, and 2 resistors R1 and R2. We want to divide DC input voltage into two parts U1 and U2, so that voltage drop across resistor R1 is 3.8 volts, and voltage drop across resistor R2 is 1.2 volts, so that our green bias dot stands exactly at 1.2 volts, in respect to the ground. We also want 1 milliampere of current running through our circuit. By some simple application of Ohm's law, we get that we need resistor R1 to be 3.8 kiloohms, and resistor R2 to be 1.2 kiloohms. In order to marry our AC signal to DC offset, we need capacitor. Don't worry, at the end of this video, there will be a messy divorce. Now, there is whole math on how to calculate what capacitor we need. Take it on leap of faith that we just need a capacitor, as its function is to add AC signal to DC voltage offset. At exit, our AC signal will now have DC voltage offset of exactly 1.2 volts. Congratulations, if you have comprehended and fully understood this, you have mastered one of the most difficult and one of the most important lessons of designing and creating amplifier circuits. Nothing is more important than this lesson about adding DC offset to an AC signal. This is paramount. Now, let's quickly draw a real amplifier circuit with NPN transistor. Let's set resistors R1 and R2 to 3.8 and 1.2 kiloohms. If we set emitter resistor to 10 kiloohms, and we set collector resistor to 40 kiloohms, we will amplify our AC signal exactly 4 times. So, our AC signal will now have point-to-point value of 4 volts. Who would have guessed that amplifiers are so simple? Now, you might be tempted to take speaker and connect it to this amplifier. That would not be such a good idea. Do you know why? Even though our AC signal is now significantly amplified, there are some problems. First, this circuit doesn't have enough power to drive full desktop passive speaker. Maximum current that this configuration of amplifier can provide is around 47 microamperes. Taking problem of power aside for a moment, the most obvious problem is that speakers require clean and pure AC signal, and although exit from our amplifier is amplified AC signal, the DC offset that we have introduced is also amplified. Our amplified AC signal now also has 3 volts of DC offset added. Speakers do not do well with DC currents and voltages. They tend to blow up. So, we need to divorce our AC signal from its DC offset voltage. We do that by adding AC decoupling capacitor. Now, if you are not familiar with relationship between capacitors and AC signals, suffice to say that when capacitance of capacitor is carefully selected, the capacitor lets AC signal to run, while blocking any portion of DC offset. Capacitor that fulfills this role in circuit is called AC decoupling capacitor, as it divorces AC signal from its DC offset. Once DC voltage fully charges capacitor, capacitor presents open circuit to DC voltage and current, while letting AC signal runs freely. In our humble opinion, this video presents and teaches one of the most important lessons in design and implementation of amplifier circuits. Grasping concepts of AC signals, and then adding DC offset, and later decoupling that same DC offset from AC signal, is paramount to fully understand and comprehend, when dealing with AC signals in general, and amplifiers in particular. Please, before you leave, show your appreciation by liking this video, leaving a comment, sharing it, and please subscribe to the channel. Thank you, and see you next time. Bye.